Hello, this is Math 280, Multivariable Calculus. I'm Professor Wheatley. Our topic today will be the chain rule for functions of several variables. All right, so we have our function of two variables. Maybe suppose that each of the variables themselves is a function of another variable t, right? So as a consequence, what we end up with here is z is f of x of t, y of t. That's composite. We need the chain rule. And we had the chain rule for single variables, so let's just remind ourselves for a minute what that is, right? So if y equals f of x, and x is some function of t, and I ask what is dy dt, right? It's d dx f of x plus d dt g of t, right? Remember, it's the old derivative of the outside times derivative of the inside, the old chain rule technique. And we can even draw a little picture here, which I think is useful. So y is our dependent variable here, right? That's sort of the final answer. And then we drop down to x, which is kind of intermediate. So x is a function of t, and then y is a function of x, so x is kind of in the middle, right? And then you kind of get this dy dx term right there. And then at the end, we have our independent variable t, independent variable t, so dx dt. And notice, what does the chain rule say? The chain rule is the product of dy dx and dx dt, right? So this is dy dx, this is dx dt. Multiply them together, get a chain rule. So our picture here from variable to variable is helpful because we can draw a very similar diagram, a little more complicated for more than one function of more than one variable. But we see how we go from dependent to independent, and along the way we pick up derivatives, which gets multiplied together. All right, let's go to the two variable case, and rather than drawing a straight line this time, we're going to draw a diamond. So dz dt, let's draw our picture. At the very top is z. Z is dependent on x and y, right? And so there's the dot for that guy. X and y are both sitting here separately, right? In other words, they're not, x is not a function of y is not a function of x. They're completely separate, but they're both intermediate. In other words, they're both functions of t. One is f of t, one is g of t, right? And along the way, we know that the derivatives we pick up are partial z partial x and partial z partial y. All right? And how do we come back together at the end? Right? X and y both depend on t, which is independent of everybody. Right? And what are the derivatives down here? dx dt, dy dt. Right? So rather than going right down the line and multiplying together, I have two separate paths which I can multiply together and then sum. And that turns out to be the chain rule. So dz dt is partial z partial x dx dt plus partial z partial y dy dt. That's one form of the chain rule there, right? And we can certainly consider it at an individual point. So let me put that over here briefly. If you have a particular value of t that you care about, so for t equals t naught, you can ask what is dz dt at t naught, right? You get partial z partial x, and then x of t naught, y of t naught, and then dx dt at t naught plus partial z partial y, also at x of t naught, y of t naught, and dy dt of t naught. So this is just a matter of plugging in. Notice that when I plug in t naught, I can plug in t naught directly to x and y, but I have to consider what the points are when I do the partials, what the points are related to those t naught values. Let's try an example. Get rid of my diagram over here. So suppose that z is square root x squared plus y squared, and let's give x of t, call it sine of t, and y of t is t squared plus 2. So you have some nice little z function. It's composite. X and y are both functions of t. Say I want to find dz dt of 0. Right? Well, I can see right away x of 0 is sine 0. That's just 0. Y of 0 is 2. Right? So I can just roll right on through, and dz dt of 0 is partial z partial x at the point 0, 2 times dx dt of 0 plus partial z partial y of 0, 2 times dy dt of 0. This is sort of slanting upwards, but see what I'm saying here, though. So I mean, this is just a matter of plugging in the point and then plugging in the point over here for the dy's, right? So what are the partials here? Partials require single variable chain rule on this guy, right? So inside the root, you have x squared and y squared, and for partial z partial x, this is like it's a constant, so it's like x squared plus 1 or something like that. So this winds up being 2x over 2 times square root x squared plus y squared. So all I need is that, right? So I need x squared plus y squared. Is that what I have here? You're good. So, and that's because we know that the derivative for the square root is 1 over 2 root x, and inside we have a 2x, and this guy is just a 0 derivative. So that guy at the point 0, 2, dx dt is just cosine t at t equals 0. Partial z partial y is essentially analogous. Just looks like that. Right? And dy dt is 2t at t equals 0. You can plug in some points here. Plug in 0, 2 here. You get 0 times 1, which is 0. And do I get 0 altogether here? Yeah, I do get 0 altogether. So, all right. I get 0 altogether here, so because this guy's 0, 2. So that's that. It's equals 0. Okay? So that's a single point chain rule. And you can check this guy out if you wanted via direct substitution. And let's see here. So you can actually plug into z and say, well, what is this thing in terms of t? Z is sine squared t. If I square t squared plus 2, I get t to the 4th plus 4t squared plus 4, like that, right? And then I could do a dz dt if I wanted to, right? So I could do dz dt, and this is just one variable now, so I would have to go ahead and let's see here. So I got 1 over 2 root all this junk. I'll just condense it into t squared plus 2 squared there. And probably, let's see, let's make this better. Times that, and then I have to do the inside derivative, so this gets slightly irritating. So this ends up being a 2 sine t cosine t plus 4t cubed plus 8t. So really, I could get a 2 out of there, couldn't I? So I could make this a little simpler. I could pull out a 2 of that thing, and I would wind up with a sine t cosine t plus 2t cubed plus 4t all over square root of all that junk, sine squared plus t squared plus 2 squared. So there's the derivative dz dt And you could, if you wanted, just plug in t here. This is probably actually faster, to tell you the truth. And certainly if this is cumbersome enough, you wouldn't want to do this. But the chain rule can certainly be a matter of convenience. It can also be a matter of necessity. Sometimes don't have a choice necessarily about what we want to do here. All right, so let's try one that we don't have a choice for, where we don't know the functions. So let's talk about baseball for a minute. Suppose you have a player and they have B at bats and H hits. That's batting average. So batting average is hits over at bats. All right, and this is typically carried to 3 places, and units are points. You talk about a 250-point batting average, 300-point batting average, et cetera, et cetera. So let's assume that H and B are functions of time. Maybe time is innings played, probably, say, i.e. T equals innings played. So depending on the number of innings played, the hits and at bats change. Certainly, these are probably not going to be linear functions. You don't always have the same number of at bats every game, and certainly people go through streaks of hitting, so we expect these to be somewhat complicated functions. But even so, let's say that, let's make the sort of generalization that suppose a hit implies H prime equals B prime equals 1. In other words, a rate of change of H is 1 with a hit. Rate of change of B is 1 with a hit. In other words, if you get a hit, it means your at bats have increased by 1 and your hits have increased by 1. And an out would be an out would be H prime equals 0 and B prime equals 1, right? Because if you get an out, your at bats have increased by 1 and your hits have increased by 0. And of course, there are some other type of things going on here. You have walks and things like this. I'm not going to get into all that. But this is pretty straightforward. Even if our functions are complicated, this derivative behavior is a pretty good approximation of what's really going on. All right, let's use the chain rule to find A prime. Chain rule to find A prime. In other words, what is the rate of change of batting average, depending on whether you get a hit or an out, things like that. So A prime is dA dt, right? This is A prime. Prime is dA dt. So it is partial H, or partial A, partial H, excuse me, partial A, partial H, dH dt, plus partial A, partial B, dB dt, right? That's what chain rule says, right? And there's 2 different cases here. There's a hit or an out. Each one has a different system for dH and dB, right? So 2 cases. Let's address the hit case first. Partial A, partial H is just like saying H over a constant, right? So H over 2 or something like this. So partial A, partial H is 1 over B, right? 1 over the constant. It's a linear function of H, right? And dH dt there is 1, so we have 1. Partial A, partial B is constant times B to the negative 1. So that's actually minus constant over B squared, right? That's minus constant over B squared, and then dB dt is also 1 there. Is this what I have there? Good. Yes. And let's see here. This winds up, if you get a common denominator, it ends up being B minus H over B squared. That's if you get a hit, right? This is how things will change. What if you get an out? Then dA dt, right? dH dt is 0, so this first term doesn't matter, right? And it's just minus H over B squared times 1, which is negative H over B squared, right? So 2 different expressions for rate of change of A, right? 1 in case of a hit, 1 in case of an out. Right? Let's take a look and see how this changes. So suppose that maybe early on in the season, so early in a season, maybe somebody has 4 hits in 10 at-bats, right? That's a 400 average. That's pretty good, right? And suppose that he gets another hit. In other words, now he's got 5 hits and 11 at-bats. How will the average change, right? So another hit raises average. Well, I can plug in here, right? So now I've got 11 minus 5, which is 6 over 11 squared, right? Raises average by 11 minus 5 over, let's see here. What I want to do is I want to do 10 minus, right? So I want to do 10 minus 4 over 10 squared. Well, let's see. Do I want to do 5 or do I want an 11? Yeah, let me do, well, here, let me do this, yeah. So this will be 6 over 100, right, which is 0.06. So your next hit is going to raise your average by about 6 points, right? So your next hit will raise average about 6 points. That's a 6. Whereas if you get an out, another out so now we've got minus h over b squared, right? So another out ends up being minus 4 over 10 squared, which is 0.04. Another out will drop average about 4 points. All right? So in other words, you'll either be raised to 406 or you'll be dropped to 396. So here, hits are definitely increasing average more than outs are decreasing it, right? In other words, early on in the season, you can raise your average pretty quickly by getting a number of hits in a row. You can get a good string together. But let's suppose for a minute here we go to the end of the season, right? So now things are low, right? So say late in the season, so maybe this is late, maybe now you've still got a 400 average, maybe now you've got 200 hits in 500 at-bats, right? So you still have a 400 average, right? Now, what's going to happen? So another hit will, how much will it raise the average by? So now you've got 500 minus 200 over 500 squared, which is 300 over 500 squared, which is about 0.001, right? In other words, another hit will raise average by about 1 point, so about 1 point. Right? How about another out, right? So every hit you get here, raise your average. You get another hit, you get about 401. Another out, what will it do? Another out drops average by, what have I got here? Minus 200 over 500 squared, which also, to 3 places, ends up being about 0.01. So again, about a point. Right? So early on in the season, you can really probably hit less than 40% of the time and keep raising your average. In other words, every hit raises about 6 points. Every out raises you about, or drops you about 4 points. So your hits are better than your outs. They raise average more than outs drop them, right? Late in the season, though, if you have, say, only a couple at-bats left, say you have 2 at-bats left, 3 at-bats left, you really have to hit it about half the time to keep your average at 400, right? If you only hit 1 out of 3, right, you're going to drop below 400, right? So you got to hit it about half the time. to keep that average up if the season's almost over. So you see that the rate of change is different as time goes by, and it makes sense depending on time. So the larger H and B are, these points will change. Okay, so that was sort of a nice kind of real-worldy example of how to approximate batting average. And it actually does do a pretty good job approximating. So if you don't know what H and T are, and it's certainly not easy to figure out those functions, even for a player with lots of data on them who's played for many, many years, likely there's going to be some unusual things going on with their functions where it changes. These will give you a pretty good way of approximating things. Okay, so let's move on to more general chain rules. How about chain rule for functions of 3 variables? So suppose you have W as a function of x, y, and z, and each one of those guys separately is a function of a single variable t. Right, so here, 3 variables, but each one is a function of one other variable. The picture is essentially analogous. Rather than having 2 branches now to go to, you have 3. You have 3 intermediate variables, x, y, and z. However, they still all link up in the end to t. Right? So there's your picture, and the partials get filled in: partial w, partial x, partial w, partial y, partial w, partial z. Down here, dx dt, dy dt, dz dt, and so dw dt is just exactly what you would expect it to be. It is the summation of these guys, dy dt, plus partial w, partial z, dz dt. So no surprises at all in the 3 variable chain rule. Absolutely none. All right, so a brief example. Let's say that w was xy plus z, and let's define x to be cosine squared. Let's define y to be sine squared, and let's define z to be t squared. All right, then we can process this through rather quickly. Partial w, partial x. Remember, this just means we fix y and z. Right? So this is like a constant function of x with a y coefficient. So that's y. All right, and dx dt is what? Minus 2 sine t cosine t. All right, and partial w, partial y is x, and then 2 sine t cosine t is dy dt. All right, and partial w partial z is just 1, because there's nothing else over here, right? So it's just 1, and that's plus a 2t. And then one could, at the end, one should really, I should say. This is dw dt, so you need to have these in terms of t, so you can jam these things in here. So this winds up being a negative 2 sine t cosine t, and the sine squared makes this a sine cubed. This is a plus, that's a cosine squared. This is plus. Actually, I guess I can get the 2 out there, can't I? I can pull the 2 out front. That's minus. Plus sine t cosine cube t, and then that is 2t is just nothing down there. Oopsies, I don't want to buy 2 though. There. So there's that. So you have the 2 out in front, and then everybody else is in terms entirely of t. Okay. So these are pretty straightforward. And you can make this kind of diagram. You can have as many functions or as many variables as you want. If they're all a function of one variable, you could just make these diamond diagrams as big and wide as you need to make them, but they have the same structure every time. They're always 3 layers, dependent, as many variables you need down here, and then independent at the end. All right, physical interpretations. We talked something about baseball. Let's go to some more physical stuff here. Suppose you have W equals T of xy. Maybe that's temperature at xy along the curve x equals x of t, y equals y of t, right? And t is time. T time. Right? So in other words, maybe you're traveling along some path, and the path temperature is changing, so this is a measure of that temperature change. All right? And in that case, dw dt is rate of change of temperature as we travel the curve. Let's try an example here. So here is some w, 3xy to the fourth, right? Say that's temperature. And let's say our curve is x equals sine 2t, y equals cosine t. I can actually draw the curve here quickly. So the curve looks something like this. Sort of has this shield shape, or an hourglass shape, I guess, like that. And you are moving always in this direction. So you're going around the hourglass like that. That's C. So there's your curve, right? Your temperature function is above it. This is some surface above this curve, right? T equals 0. I plug in t equals 0. I get 0, 1. So I'm starting here, right there on the curve, right? And W at 0, 1 is 0, right? It's 0. So the temperature there is 0. Maybe some base temperature, I don't know. But we can ask, what is dw dt at t equals 0, right? It's partial w partial x at 0, 1 times dx dt at t equals 0 plus partial w partial y at 0, 1 times dy dt t equals 0. And that's almost visible over there, but 0. So there you go. So there's this expression. We know that from earlier. This is a pretty easy function to deal with. Derivative-wise, the partials are simple. Partial derivative there is 2xy plus 3y to the fourth. And that is evaluated at 0, 1. Dx dt is 2 cosine 2t at t equals 0 plus partial w partial y is x squared and 12xy cubed, and then times minus sine t at t equals 0. Yeah, okay, so if you plug all this junk in theory, if my work is right, I get 6. So maybe this is in degrees per hour, something like that, right? Because it's a rate of change, but it's not a temperature, right? The temperature is 0, but as you move away from there, you are changing by 6 degrees an hour. Notice this is a change on the surface, not on the curve. The curve is pretty flat up there. It's not the change there. It's not much change in movement, but this is not temperature. This is just the curve. The temperature is changing by 6 degrees an hour. And actually, could even be more concrete about it. We can say, note 6 is the slope of the tangent to the curve. And if I jam in everybody up here and make this a function of one variable, what on earth do I get? I get sine squared 2t times cosine t plus 3 sine 2t cosine to the fourth t. If I were to graph this in 2 dimensions, right? So if I made a picture of the TW plane, I would see that 6 would be the tangent line slope, right? So it's rising by approximately 6 degrees per hour when we're at this point on the curve. The surface temperature is rising. So as the bug moves along, you can expect temperatures to rise by 6 degrees an hour at that point. Okay. So that's that. We can extend this a little bit and maybe even chalk in a couple more variables here. So what happens if we have a function of 2 variables, but each of those variables is also a function of 2 variables? So maybe a way to view that would be you have a flattened map. I'm saying a flattened globe, yeah. You have a flattened globe, and you overlay an XY grid, and you say to yourself, all right, I want to pick a longitude and a latitude, and that determines a point on my map. So you choose a choice of longitude with latitude that gives you an XY point on the grid, and then I ask, well, then that point has a temperature along with it. Yeah, let me say it up here. Maybe I'm not saying quite what I want to say. So this is still temperature. So let's let W still be temperature at XY. Now we have X being a function of both R and S, and Y being a function of both R and S, right? And so, yes, I see. So in other words, maybe let me try to illustrate here. You have a flattened globe, right, with an XY grid, right, and you let longitude be R and latitude be S, right? Then your positioning on the x-axis depends on both the choice of longitude and latitude. In other words, along the x-axis, maybe you run along a single line of longitude, but maybe you have many, many lines of latitude there, and so you pick one R and one S, and that gives you one point on the x-axis, and R and S also give you a unique point on the y-axis, right? And then so now you're at some point in x, y, you're sort of off the map. So the map is these lines, R and S. Now you're at some point on the XY grid, right? So XY grid is different than the map. And so now your surface temperature there is still a function of X and Y, but they're both separately a function of 2 variables, right? So you have something like that. So your temperature surface is above everything. So you have your flattened map, which is R and S, and your XY grid, and then above that there's some surface which gives temperature at every XY point. Right? Now, W no longer has one derivative. It has partials. So now W has 2 separate partials, as partial W partial R and partial W partial S. Right? Each one of these guys has a chain rule attached to it. Let me come over here. So each one of those guys has a chain rule, right? And each one of them has a different diamond picture, right? Here is the first picture. So W is dependent, X and Y intermediate, R is independent. In other words, you can take the partial with respect to R, and this is like saying that the functions are just functions of R. S is a constant, right? So these are just functions of R. This is the picture that you get, right? And so we see partial W partial X, partial W partial Y. Down here, excuse me, not partial, but partial X partial R, partial Y partial R. Notice I need partials all over here because these are functions of 2 variables. They don't have one derivative, right? And we also have the same picture, just with a different closing point. So W, X, and Y are all the same, Down here is s, though, the other independent variable. So partial w, partial x, partial w, partial y. Down here, partial x, partial s, partial y, partial s. Right? You have both of those guys, right? And so these are two separate things that we have existing here, depending on which partial we're referring to. We're not going to combine the two of them. It doesn't make sense to do that. But we do have two separate partials. Right? So we know partial x, partial r, plus partial w, partial y, partial x, partial y, partial r. So that's the first diagram. Is that guy? Partial w, partial s is partial w, partial x, partial s, plus partial w, partial y, partial s. That's the second diagram. Each one of these diagrams is a separate instance of the chain rule. It's not a combination like it was before. These are separate instances. Let me do a brief example of this. We won't spend too much time on this, but it's good to see it once. Suppose that w, this is example, w is a 4x squared y cubed. There's my temperature function. I determine my x's by the following, and my y's by the following. So x is r cubed minus s sine r, but it's not a s sine, it's s sine. And y is 4r squared. So maybe this gives the location based on longitude and latitude, and this gives the location also based on longitude and latitude on the grid. Okay. Let's see here. So partial w, partial r is simply following this rule, right? So partial w, partial x is 8xy cubed. Partial x, partial r is 3r squared minus s cosine r. All right. Then we have partial w, partial y, which is 12x squared y squared. Partial y, partial r is 8r. Is 8r. I think it looks good there, yes. So there's your partial expression for that one. And we can do partial w, partial s too. The partials with respect to w, x, and y are the same. What changes are now we have partial x, partial s, right? That's just minus sine r. And everything's the same down here, except now we got partial y, partial s. There's no s in there, so it's just 0, so that goes away. So you have those guys here, right? And if you wanted to, I mean, what's really good here is to express these in terms of r and s. You really should do that, because we're talking about partial with respect to r and s. So I really should fill in for x and y here. I'm not going to do it, though, out of sort of laziness. But what we can do is, if we just care about a point, we don't need to do that. We can circumvent this issue. So I can still evaluate these, can evaluate at a point rs without subbing in for x and y, and that may be quicker. So supposing, for example, I want rs to be pi comma 0, what is my xy point? My xy point is pi cubed minus 0 for the x value, so pi cubed. And my y point is a 4 pi squared. Right? That's what I've got good. And so now I can say, well, partial w, partial s at the point pi 0, rather than having to go through and sub everything in, I can just sub in these points, right? So I can say, well, this is what's x? Pi cubed, and then 4 pi squared cubed. What's 4 cubed? 64. Yeah, so that's 64 pi to the 6th. Negative sign of pi is 0, so this whole thing is 0 anyway. I don't need that, though. What am I working here? I'm working. Yeah. Well, actually, let me work partial w, partial r. So everything else is the same first, but so this ends up being times 3 pi squared minus s cosine pi, which is a positive s. What's s? 0? Yeah, plus 0. Yeah, I'm getting lost in my own. Well, yeah, here we go. So we're down here, yeah. And this is 12 pi cubed squared is pi to the 6th. Y squared is 16 pi to the 4th. So 16 pi to the 4th. And then times 8r, which is times 8 pi. So what on earth is all of this? Well, it's a lot. It's something 8 and 64 is. Do I have an answer here? I claim it's 3,072 pi to the 11th. And probably I'm right. So that looks good. So you can do that without having to actually plug in for x's and y's over here. Okay. So sometimes a shortcut. All right. The last topic of this section, actually, we're going to come back to implicit differentiation. We tackled this in 14 or in the last section, implicit and partial derivatives. What I want to do now is make something that streamlines the process, and also not only streamlines it, but also makes it easier to have this analog for higher dimensions. So let's examine implicit differentiation. I think that those that have struggled with it in the past will appreciate this when they see its simplicity. So here's z equals f of xy. This is differentiable, right? And let's let this equal to 0. Define y implicitly, yes, as a function of x. Function of x, i.e., let y be h of x. Right? So in other words, what I'm saying is, if I let z be 0, this is just x's and y's in here, right? So I have some thing involving x's and y's equals 0. Maybe I can't solve it for y. That's okay. But I can let it be implicit. So maybe an example is good to see here. As an example, suppose I began with this function of 2 variables. Also, these should be differentiable too. I mentioned that earlier, I think, but I mean, you don't want to have problem with differentiability, otherwise you're going to really have issues here. So here's a function of 2 variables. This is a surface, but suppose I let z be 0. I look at the level curve when z is 0. And that's the xy plane, right? This is just a curve in the xy plane now. What I get is this thing. I get this, which is just in the xy plane. I can't solve it for y. That's not possible. But I certainly, if I want to get the derivative here, I could do implicit differentiation, just like we did in Calc 1. So that's what I'm saying here when I want this to define y implicitly as a function of x. Maybe it defines it explicitly. I don't know. If it does, then this is not really needed. But if it defines it implicitly and I can't get it explicitly, I need to do this process. All right. So I have this idea. What is the chain rule? So how does it help us? Let's draw a picture. Let's make some room here. So up at the top, here is our z, right? So there. And z, our usual chain rule diamond. There's x and there's y, and our usual derivatives follow suit. So partial z, partial x. But notice now, I mean, I'm saying y is a function of x. Even if it's not explicit, it's implicit. So at the bottom of this here it's not a factor, so it's not anymore x and y are both functions of t. Now it's y is a function of x. So what's independent down here is actually x again. So notice, what do we have here? The usual dy dx. This is usually dx dt. It's dx dx, right? And think about it. The derivative of x with respect to x is 1, right? Think of it so in other words, x derivative is 1, right? It makes sense, nothing more to say about that. So if I have my position z equals 0, and let's say I differentiate both sides with respect to x, right? In other words, I do d dx z equals d dx 0, right? That's what I'm doing here. It's like I used to do with implicit differentiation. I took d dx of both sides, right? What do I get? Well, this guy over here, follow the chain rule. Follow the chain rule. I get partial z partial x, dx dx. That's unexciting because it's 1. Partial z partial y, dy dx equals to 0, right? Because this is the chain rule applied to z, right? This is the chain rule applied to z. And so I can now solve. I can say, well, what is dy dx? It is negative partial z partial x over partial z partial y, right? Because what did I do here? This was just 1, right? So when I isolated this thing, right, I moved this guy over and I divided by that guy. And sort of a shortened way of saying that is sort of this, is that subscript. We don't really use this that much, but that sort of subscript notation, right? F sub x as long as f sub y is not 0, all right? So that is a very nice, simple way of doing implicit differentiation, right? In other words, if we're stuck with somebody who's a Calc 1 problem and we're having trouble differentiating implicitly, if we think of it as a Calc 3 problem, this technique can work. It's very, very, very straightforward and easy. What's even better is that this extends. And that's, in fact, why we like to talk about these things, is because this not only makes things easier, but it extends to higher dimensions without difficulty. The other technique of doing things where we kind of muddled through the algebraic stuff, not so much. So let's try a 3-variable case. How about a function of x, y, and z equals w equals 0? We did a problem like this in the last section where I had a function that had x, y, and z was implicitly defined as a function of y and x, not explicitly. And I had to do implicit differentiation on it. Maybe that was troublesome for some of us, but now we'll see a process that makes this very straightforward. So again, I have here a function of 3 variables. This is a 4D thing, w. I'm looking at a level surface of it. I'm looking at a level surface. In other words, this defines z implicitly as a function of x and y, right? So this is a level surface. And again, we will start with w equals 0, and we will take partial w partial x and partial w partial y of both sides, because x and y are both the independent variables, right? In other words, what we have here is w a function of zx and y, and then we're considering z implicitly as a function of x and y being unrelated. They are unrelated variables. They're both independent. So really we need 2 pictures here. I'll draw one, and we can certainly extrapolate to the other. Partial w partial x, what have we got here? We've got at the top big W, right? Down below w, there are 3 independent variables, x, y, and z. But we're considering z as a function of x and y, right? So when I come down here, let's see if I can make this connect up, right? What we have to consider here, let me fill in my partials up here. This is partial w, partial x, partial w, partial y, partial w, partial z. I've got 3 independent variables, but in terms of the partial x's, I mean, x is the one I care about. Y is unchanging, right? So this over here has to be a partial, right? Because in particular, z is a function of both x and y separately. It doesn't have one derivative. But everybody gets a partial x, partial y, partial x, partial z, partial x. Some of these guys are very easy. Partial z, partial x, it is what it is. Partial y, partial x is 0 because y is not a function of x. X and y are independent of each other. This guy, y is not a function of x. There's nobody x in there. So this guy is 0. And partial x, well, that's just 1, right? Because again, it's the same as dx over dx. It's 1 there, right? This is because x and y are independent. Here, it's just because x is dependent on itself only. So from w equals 0, right, what do we wind up getting here? So we take partial w, partial x of both sides of this equation. On this side, let me write it here. So partial w, or a partial x of w equals partial x of 0. Over here, the chain rule guides us. So this is partial w, partial x times 1, right? So partial x, that's 1. Partial w, partial y times partial y, partial x, 0. So lots of these guys are going to go away, essentially. Partial z, partial x, right? This, and this is equal to 0. This becomes 1, so we get partial w, partial x. Middle term drops out. It's got a 0 in it. It's gone. Plus partial w, partial z, partial x. Right? I can solve for partial z, partial x. This is equal to 0. Can solve for partial z, partial x. Right? Just scoot this guy over and divide, and we get partial w, partial x over partial w, partial z. Right? Yes. And notice the variables in question here are the same variables in question here. There's no y anywhere in this. I can rewrite this as negative f over x, f over z. And notice it looked just like we had previously when we only had the 2-variable case. We had negative fx over fy. Right? Same idea there. And also, we could do the exact same. We could play the exact same game with partial w, partial y, draw the same picture. This time, this guy is 0, this guy is 1. So let me say similarly. It's a good exercise to check this on your own. Partial z, partial y is going to be negative fy over fz. Like that. That's a nice result. And we can keep on doing this for as many dimensions as we want to. Just draw the picture. Look at the way things are going. Lots of things will cancel out and get what you want. So let's apply our newfound knowledge here. And let's go back to an implicit differentiation problem of 2 variables and see if we can't make it easier. So what have I got here? Let's given xy squared plus z cubed equals negative sine xyz. That is certainly z is a function of x and y implicitly and not explicitly. Okay. So to make this work, I've got to get myself in a position where I've got somebody's level surface. Right? this is a level surface of a function of three variables, right? This is the, if this is W, then this is the zero level surface of that, right? It is the thing in space, some surface in space that exists here. Okay? Let's see if I can't find partial z, partial x. I need f sub x. In other words, I need to figure out what the partial with respect to x of this guy is. So I get y squared. There's nobody over here to deal with. He's gone. And then I wind up with yz cosine xyz, because this is both of these guys act like constants, right? Both y and z are like a constant. Okay? I can get fy. Actually, I'll find both the partials. So let's find both partials. We want partial z, partial x, and partial z, partial y. So fy, we can do this too. We get a 2xy. Nothing happens here. This is xz cosine xyz. And partial f partial z. Nothing happens over here. This is 3z squared. And this is xy cosine xyz. Right? And so now, that was very short and easy. Now we just go ahead and plug into our formulas here. Partial z partial x is minus fx over fz. So we end up with minus y squared plus yz cosine xyz, and 3z squared plus xy cosine xyz, partial z partial y minus fy over fz, negative 2xy plus xz cosine xyz, all over 3z squared plus xy cosine xyz. So there are your partials. So pretty straightforward. Okay, that's it.